Well, hey there, team. Are you ready to look at another kind of different sort of concentration unit you may not have run into? You probably heard this one before. A lot of times, if I'm pushed for time in a lecture, I'll skip this, but this is a really big one if you move on to become a chemistry major, maybe get into environmental chemistry, atmospheric chemistry, something like that, or if you deal with solutions with very, very low concentrations, right? Because we've learned percent units and molarity and whatnot, but what if we had not like a 5.2 mass percent solution of sodium chloride? What if we had a 0.00000035%? What? That's too many leading zeros. It's not practical, right? So there's quite a few of these solutions that are very, very dilute, or different types of applications. Like I said, atmospheric, environmental chemistry. If we're looking at concentrations of species, I'm looking outside my window. You're wondering, breathe in, it's about we always say 78% nitrogen, about 21% oxygen. But everything else is that tiny, tiny little bit. So what's the concentrations in the atmosphere of, things like carbon dioxide, hydroxyl radicals, maybe certain types of pollutants where they're incredibly small numbers. We need some new concentration units for that. Although these aren't technically new mixing ratios, you've been working with a mixing ratio or a relative concentration unit using percentages. So I have ppm, ppb, ppt up here. My class, you're probably familiar with ppm, or parts per million, when we did precision and uncertainty, where you take this ratio, multiply it by a million to get, parts per million error, or part ppt, parts per thousand error. So PPT typically means parts per trillion when you're dealing with mixing ratios. When you're dealing with error, usually it's going to be parts per thousand. Some people go PPTH for parts per thousand. So here's these new units here. Think of them like percentages, where a percent is a parts per hundred, right? At least in my class, I taught a percent is a part over a whole. Right? Here's the whole amount in the denominator. Here's the part we're interested in the numerator. It's just a ratio of a part over whole. And if we assume 100 parts of the whole thing, like in the last video we talked about 40% vodka would be 40 milliliters of this ethanol over an assumed 100 parts, or 100 milliliters. That's a volume percent. Well, what if you've got a really low percent value? And this isn't terribly low, but we could get a lot lower than this. So I was poking around, current carbon dioxide levels. People are concerned about that as a greenhouse gas and whatnot. They're pushing about 0.0417%, but that's an awkward number, 0.0417. You won't usually see that in the literature. You'll see a different term. But let's think of the percent as a part per hundred. So how would we set this up? Or pph. Nobody ever writes pph. This would mean if I had 100 particles of air, our solution is a gas phase solution, right? 0.0417 molecules of CO2 would be in that. If for every 100 particles of air I pulled out, 0.0417 would be CO2. That doesn't make sense, right? 0.0417 molecules of CO2, that's just weird, right? It's not practical. So watch what I do here. Well, let's get this into a number that makes sense, like a 4, a 41, a 417. So why don't we get that to 417? So let's multiply that by 1, 2, 3, 4. Multiply the numerator by 10 to the fourth. And if we do that, let's multiply the denominator by 10 to the fourth. So if we take 0.0417 times 10 to the fourth, we get 417 molecules of CO2. If we take 100 times 10 to the fourth, we get 1 million, right? 1 times 10 to the sixth particles of air. That's why in atmospheric chemistry they call it a mixing ratio. We'll apply this to solutions in a second here. So this is a little bit easier to say. For every 1 million particles of air or solution, 417 would be molecules of CO2. That just sits better with me, right? Hopefully with you as well. So if 0.0417 over 100 is parts per hundred or percent, then 417 over 1 million would be ppm, or parts per million, right? Or if it was over 1 times 10 to the ninth, it'd be parts per billion. If it was over 1 times 10 to the 12th, it'd be parts per trillion. So in atmospheric chemistry and environmental science, you can pick the denominator to make the numerator a nice number, right? So if it's too big or too small, you can adjust that to parts per million, parts per billion, parts per trillion, parts per hundred, parts per thousand. Hey, we can kind of morph it to whatever we need, right? So that's a cute little thing. Let's throw another atmospheric one up there. It gets you to think about it a little bit, and then we'll look at some solution parts per million units. So here's another example you may have heard of, especially if you live in Southern California like I do. Smog alerts, right up in LA. So LA was famous a long time ago for having some of the worst pollution in the world. So we have pollution named after us, LA smog, or photochemical smog, where ozone can build up to unnaturally high levels, which are it's not good for you. I'm not here to get into the physiological effects of ozone, but you think of the ozone layer, which is just a section of the atmosphere way up, but there's ozone. So ozone up there, good. Ozone down here in the troposphere, not so good. Ozone in the stratosphere, good. Ozone in the troposphere, not so good. You don't want to be breathing it. That's why my the windshield wipers here, the rubber, I mean, you got to replace those fairly, I mean, compared to like other places, fairly often because they get hard and cracked and things like that. You know, thank you for the LA smog. So we get these smog alerts. Now, natural ozone in the troposphere, I mean, you might be pushing, 20-ish parts per billion, or ppb. That's the terminology an atmospheric chemist would use. But in some of our smog alerts, we get 440 or higher, 100, 200 to 300 parts per billion. You're like, all right, nobody's going to school today, right? Because it could be a health hazard walking around in that kind of environment. But let's see, what would that mean, 40 parts per billion, if we wanted to write that as a mixing ratio? That would mean, so 40 ppb is parts per billion, right? Parts per billion. I can't help but think of Dr. Evil when you think of 1 million, 1 billion. So what does that mean? Well, just like a percent would be a parts per hundred, if I had 1 billion, 1 times 10 to the ninth, 1 billion particles of air, of that, how much would be the singular component we're interested in? Ozone be 40. So we'd have 40 molecules of ozone. So that's what that means as a mixing ratio, right? So 40, and parts per billion works better. Parts per million probably wouldn't work really well because there's much less ozone than there is carbon dioxide. Carbon dioxide is it's not like a major, but it's up there. It's not like nitrogen and oxygen. So parts per billion works for ozone, but it doesn't work for nitrogen or oxygen or carbon dioxide or something like that. See? So useful little things, but that's just how to set it up as a ratio, just like we have been doing with percent for a long time. You can literally throw a percent up here and review that video if you need to. Let's look at it when we're dealing with things like aqueous-based solutions, right? This is more for the atmosphere. So let's look at it in terms of like volume units of solution. How would we make that change between this kind of terminology, parts per million, parts per billion? What would that be in terms we would see in a normal lab? Let's do that on the next board. When we're looking at solutions, right, typically what we think of as a solution in general chemistry is not air, right? We typically go, you say solution, we think of a liquid solution, right? A dilute sodium chloride solution, or a potassium nitrate solution, something like that. So when we're dealing with that, it makes sense to go, so many particles of solute per particles of solution, like we would atmospheric chemistry, like out of 1 million particles of air, how many molecules of that particular species. Makes more sense for atmospheric chemistry. So let's relate these mixing ratios or relative concentrations in ppm, ppb, whatever, to something more comfortable with us, right? So like mass of solute over volume of solution, those kinds of things. Well, let's take a look here. Let's start with 1 part per million. What would that mean in terms of our ratio? Well, that would be for every 1 million, right, of the whole, you'd have 1 of the part. And if we do that in terms of mass, that would mean we'd have 1 gram, like if we did a mass percent. Like if I had a 0.52% by mass, it'd be 0.52 grams of solute per 100 grams of solution, right? So no difference. We're just doing a very, very dilute one. So 1 part per million by mass would be 1 gram of solute for every 1 million grams of solution. That's our setup, right? Well, let's convert the mass of solution to volume of solution, which is typically what we do in a lab. We've got to make an assumption here on the density. If we want to go mass to volume, we need density, right? Now, these are extraordinarily dilute solutions, almost all water. So let's assume we're roughly room temperature. Densities are the 0.997, 0.996, 0.998 grams per milliliter. Well, to two sig figs, we could probably go 1.0. To 1 sig fig, we could easily go to 1. Right? Everybody okay with that? So for very dilute solutions, we can estimate the density as 1 gram per milliliter. We technically could go 1.0, but we're not dealing with sig figs in this one. So that allows us to eliminate, let's do it in green, grams of solution. Boop! And now we're in grams of solute per milliliter of solution, but it's still a really awkward number. So let's convert milliliters to liters, and let's get the volume of our solution into liters in this case. So milliliters of solution to liters of solution. So this would give me grams of solute per liter. But let's do, now do you see how the 1,000 times 1,000 cancels out? The million, 1,000 times 1,000. So it's going to be the same number. That's my goal. What's the same number, numerical value, in a different type of unit? So let's take the grams of solute, convert to milligrams of solute. You see that? So the 1,000 times 1,000 cancels the million. Hey, so we get 1, 1, 1, 1, 1, 1, 1. So 1 part per million is the same as 1 milligram of solute per liter of solution, with the assumption that the density of that very dilute solution is 1 gram per milliliter. Cool. So you'll commonly see this in labs. People make quick conversions. They go, oh, 1 part per million. That's the same as a milligram per liter. What I'd like you to do is do the exact same thing I did, but do it for ppb, parts per billion, and parts per ppt, parts per trillion. See what you get. Make sure you keep liters in the denominator and see what units of mass you would need in the numerator to make that work out. Did you do the same thing for the other two? Part per billion and part per trillion? So ppb, probably one of the more common ones in atmospheric chemistry and stuff. And environmental chemistry, you'll see environmental chemists do this with solutions, very dilute solutions. Well, just like a percent, right, would be parts per 100. This would be parts per billion. So that would be, by mass, 1 gram of solute for every 1 billion grams of solution. Let's convert that solution to liters. So assume a density of 1 gram per milliliter. And we can cancel out our units and convert milliliters to liters. So we got liters of solution in the bottom. And then what number do we have to put here? What unit of mass do we have to convert it to so that we get a number of 1 on both sides? All right, so we got 1 times 10 to the 9th. All right, well, we got 1,000 here, so that makes that 1 times 10 to the 6th. So we need 1 times 10 to the 6th times 1,000 to give us 1 times 10 to the 9th to cancel out. See that? So 1,000 times 1 million is 1 billion. Those cancel out. That would have to be micrograms. So that means is 1 part per billion is the same thing as 1 microgram of solute per liter of solution. So grams of solute cancels. Or 1 pp is just 1 microgram per liter. Nice little shortcut they use. Do the same thing for ppt. Now, if you've taken my labs, we have used ppt as parts per 1,000. All right, technically, we probably should use ppth, because now we're confused. Is ppt parts per 1,000 or parts per trillion? Oh, no. So if it's not specified, look at it in context. Right? If you're looking at atmospheric chemistry or an extraordinarily dilute solution, it's probably parts per trillion. If it's a normal, if you're doing calculations with precision accuracy or a not so dilute solution, probably parts per 1,000. Okay, so here we go. It's the context. So in my class, if it's dealing with solutions, it's probably parts per 1,000. If it's dealing with statistical analysis of data, it's probably parts per 1,000. So parts per trillion for solutions, parts per 1,000 for statistical analysis of data. We good? So ppt, or parts per trillion, right, would be 1 gram of solute per trillion grams of solution. Let's convert the solution to liters, right? So assuming a density of 1, converting milliliters to liters. And then we go, okay, well, what number do we need here to cancel out the trillion? Well, we have 1,000, so 1,000 times a billion, right, cancels out the trillion. Boop. 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 Right, so 1,000 times 1 times 10 to the 9th is 1 times 10 to the 10th. Bye-bye. And then to do that, that would be nanograms. So there's 1 times 10 to the 9th nanograms of solute per gram of solute. Cancel out grams of solute. And you're left with nanograms of solute per liter of solution. Or the shortcut term, 1 part per trillion is 1 nanogram per liter. Whew, crazy. Most people don't bother with this. They just memorize that and they're off to the races. We're not going to use this hardly ever in my class, but if you move on as a chemistry major, you'll probably be exposed to these types of units quite often. All right, there's your exposure to some parts per million, parts per billion, parts per trillion, even though we've already done percent or parts per hundred.